In this video segment, we demonstrate techniques for interactive cut and paste editing of multi-resolution surfaces. The basic idea of pasting is quite simple. The user selects an area of interest on the source surface, in this case a drop of wax on the candle model. The user then specifies a location on the target surface, in this case the face where the feature is to be pasted, and interactively adjusts its position, orientation, and size. We now illustrate the main steps of our algorithms in more detail. The first step in the pasting process is to separate the parts of a surface that constitutes detail to be transferred from the larger scale surface shape, which should be ignored. We separate both the source and target models into base and detail surfaces. Through pasting, the detail part of the target gets replaced with the details of the source. We provide the user with a continuous range of base surface choices which he or she can control through a single parameter reflecting the flatness of the base surface. This example shows the result of pasting for various choices of base surfaces. This sequence illustrates the corresponding base surfaces on the source model. The next step of our algorithm is to find a map from the source base surface to the target according to which the details are transferred. For this purpose, an area on the target surface must be identified and parameterized. To find a suitable target region, we represent the boundary of the source feature in radial form, and we use geodesics on the target to map feature boundary points onto the target surface. This example illustrates the radial paths used to identify a butterfly-shaped region. As the position of the feature on the target is modified, the target region is recomputed on the fly. The next step is to parameterize both source and target regions onto the plane, align the two parameterizations, and resample the source surface over the target sampling pattern. The source parameterization is shown here in black and the target one in red. As the feature is being scaled on the target, its parameterization is being recomputed. Note that in some cases, adaptive sampling is more suitable, as shown in this example. In this example, we show the pasting of a complex feature, an ear, onto a head model. As before, adaptive resampling considerably improves the quality of the final result. Our final example shows how the medium-scale detail of a logo feature can be pasted on a rock model, with and without preserving the small-scale surface details of the rock.
In this video, we present our method for dual contouring Hermite data. This footage was captured on a consumer-level PC in real time. We begin with a simple example of a mechanical part. An implicit description of the part was generated from a subdivision surface via a scan conversion algorithm. Here you can see the underlying uniform grid that describes the surface. Vertices of the grid are signs represented here as spheres and boxes, for inside and outside respectively. Those edges that contain a sign change are tagged with an exact intersection point and a normal shown here in green. Polygon generation proceeds in 2 steps. First, our method constructs quadratic error functions for each cube from the Hermite data on its edges and calculates one vertex per cube at the